Good afternoon, class. We are looking at Chapter 2, Review Limits and Derivatives. This is, for example, one covering 2.1 to 2.8, and here's the second part covering 2.4 to 2.6. 2.4, the precise definition, 2.5, continuity, 2.6, limit at infinity, horizontal asymptotes. Two point four, the precise definition. The limit of f of x as x approaches 3 equals 5. It means f of x is close to 5 when x is close to 3. So when you look at the graph, okay, f of x is close to 5 when x is close to 3 in some close distance to 3. That's where you find x between 3 minus delta and 3 plus delta. And you find f of x to be close to 5 by epsilon. So 5 plus epsilon, 5 minus epsilon. Both of these numbers are Greek letters and they represent small numbers. We can make the value of f of x within an arbitrary distance epsilon from 5 by restricting the values of x to be within distance delta from 3, but x is not equal to 3. That's the idea, within delta. And this is within epsilon. If x is between 3 minus delta and 3 plus delta, as you can see it here, x can't be equal to 3. Then f of x is between 5 minus epsilon and 5 plus epsilon. So f of x is somewhere here. By taking the values of x is not equal to 3 to lie in the interval of 3 minus delta and 3 plus delta, as you can see from the graph, we can make the values of f of x lie in the interval of 5 minus epsilon and 5 plus epsilon, as you can see. In other words, remember the concept of a limit refers to the y coordinate, okay, of the function. So, precise definition of limits. Let f of x be a function defined on some open interval that contains a, except possibly at a itself. We say the function has a limit at a, or limit of f of x as x approaches a equals L. If for every small number epsilon larger than 0, there is a number delta larger than 0, also very small, such that if the absolute value of x minus a is between 0 and delta, in other words, the x minus a represents the distance x has from a, then absolute value of f of x minus n must be less than epsilon. Now, what we have said here, the synopsis of that is here. So I'm going to read it for you. And the notations. This notation, whatever epsilon larger than 0, there exists a delta larger than 0, such that if absolute value of x minus a is less than delta, it results that absolute value of f of x minus L is less than epsilon. And a, so the x is somewhere between a minus delta and a plus delta, where f of x is somewhere between L minus epsilon and L plus epsilon. That's the precise definition. So this notation in math, it's read whatever. This one reads exist. There exists. This short line segment is read such that. So let me read this one more time for you. whatever the value of epsilon larger than 0, there exists delta larger than 0, such that if the absolute value of x minus a is less than delta, therefore the absolute value of f of x minus l is less than epsilon. That would be the result. Example, use the graph to find delta such that absolute value of x minus 3 is between 0 and delta. It results in absolute value of f of x minus 2 is less than 0.5. And I like to go with this definition that I gave you. That makes it very easy. The concept is this: guessing any value for delta given epsilon larger than 0, we need to find or guess delta larger than 0 such that if absolute value of x minus a is between 0 and delta, then absolute value of f of x minus l is less than epsilon. Of course, the graph really indicates that, for example, f of x is between 1.5 and 2.5, and x is between 2.6 and 3.8. However, let's always restart with f of x minus l less than epsilon. So with that being the case, so we put f of x minus 2 less than 0.5. This is what we start, the second part. And as you recall, the absolute value property, if absolute value of x is less than a, assuming a is positive, then x is sandwiched between minus a and a. So the same thing happens here. So it's sandwiched, f of x minus 2 is sandwiched between negative and positive 0.5. And we are going to add 2 to 3 sides. And of course, this you can read it from the graph, okay? But the purpose of that to show you if the graph is not given and you have to figure it out from here, this is the process. Now, and you can see from the graph that x is somewhere between 2.6 and 3.8. So you have to look at the distance here, okay? And you have to look at the minimum of the two, 3 minus 2.6 and 3.8 minus 3. So the distance between these two, this distance is 0.4, this distance is, so this is 0.4, right? 3 minus 2.6. And this is what, 3.8 minus 3, or 0.8. You have to choose the minimum of the two, which is 0.4. And any smaller number than 0.4 will do, and notice x can't be 3. Why is it that we have to choose the minimum? Because if you choose the maximum, if you choose 0.8, and therefore you go 0.8 on this side, then it will take f of x outside the range of absolute value of f of x minus 2 less than 0.5. So whenever these two numbers are different, the distance from 3 to those two numbers are different, you choose the smaller of the two. And any number smaller than that will, of course, do the job. Example 11, prove that the limit of 4x minus 5 as x approaches 3 equals 7. Remember, we basically plug in, but if we want to prove it using the definition, okay, remember what we say here, guessing a value for delta given epsilon larger than 0, we need to find or guess delta larger than 0 such that if absolute value of x minus a is between 0 and delta, f of x minus l, the absolute value is less than epsilon. So we're going to write this and we're going to plug this in and we're going to start with the second part. So as we write this, we are going to know that a is 3, everybody. L is 7, right? So replace the a with 3 and replace the f of x with 4x minus 5 and L with 7. So this is your function. So we are going to do so. If absolute value of x minus a, which is 3 less than delta, then absolute value of f of x, which is 4x minus 5, minus L, which is 7, is less than epsilon. The idea is to find a relationship between epsilon and delta by manipulating the second part to look like either this or multiples of that. So that will give us 4x minus 12. So we start always with the second part, and that is absolute value of 4x minus 5 minus 7 gives us absolute value of 4x minus 12 less than epsilon. We notice we can factor the 4 out. Now, whether you keep the 4 inside or outside, the absolute value makes no difference. Because the absolute value of 4 is positive, you can take it out. And so if I divide this both sides by this number, I get absolute value of x minus 3 less than epsilon over 4. Now, this and this one, I'm going to compare. This one, okay, so compare to absolute value of x minus a less than delta compared to this. When you put them next to each other, left side is identical. The right side says, if you choose delta to be epsilon over 4, you're in good shape. According to these, choose delta to be epsilon over 4. Practically, we're done. Now we're going to show that this thing works. And so we are going to go back here and we're going to plug in and we get to the right side. So we show that this delta works by going with the reverse steps, starting with this one and choosing sigma to be epsilon over 4. So we start with this now, and we say the choice is that delta is epsilon over 4. And because it's epsilon divided by 4, we're going to multiply both sides by 4. So we put the 4 here, and this becomes 4 delta or epsilon. So this is 4 times that, or this is epsilon. By the way, whether you put the 0 or not, you can keep it if you want. It makes no difference. We are interested in this part. Now, we want this to look like that ultimately. So we're going to take the 4 inside, becomes 4x minus 12. And we want it to look like that. 4x minus 12, everybody, is the same as 4x minus 5 minus 7, isn't it? So we write this as 4x minus 5 minus 7. So we made it look like that. And so from here, we ended up here. So we're going to write this one in conjunction with this one. And then we just proved if the absolute value of x minus 3 is less than delta, the absolute value of 4x minus 5 minus 7 is less than epsilon. And that is, again, the reverse process. We are going back, we are going back, we are going back, shows the limit of 4x minus 5 as x equals 3 equals 7. And if you were to look at the graph, if you add and subtract sigma from 3, so that would be where x lies somewhere between 3 minus delta and 3 plus delta. Then 7 minus epsilon and 7 plus epsilon, that's where the function lies, the limit of the function. So that's the reverse process and the proof. (2.5) continuity. Here's the summary. A function has a limit at a if the limit of f of x as x approaches from the left is L, and that is equal to the limit of f of x as x approaches a from the right. Therefore, the limit of f of x as x approaches a becomes L. Direct substitution property. For polynomials or rational functions, if the function exists at the value a, then the limit of the function as x approaches c is equal to function's value at a. Limit of f of x as x approaches a equals f of a. A function is continuous if the limit of f of x as x approaches a equals f of a. This is the definition of a continuity. A function is continuous from the right if the limit of f of x as x approaches a from the right is f of a. A function is continuous from the left if the limit of f of x as x approaches a from the left is f of a. The intermediate value theorem, also known as IVT. If f of x is a continuous function on the closed interval of a to b, and let n be any number between f of a and f of b, where the two values are not equal, there must exist a number c in a and b such that f of c equals n. What is IVT? IVT says if we know the function is continuous, there is no break. And if we know it's a closed interval of a to b, so continuous and closed interval, that means we can see the endpoints easily. It doesn't go indefinite. If there is a number between the two functional value, the endpoints, f of a and f of b, there must exist a number. There is a f of c in between. This is normally used when we want to find x-intercepts and so forth, okay? Because it helps to find if one value is negative and one value is positive. So 0 must be in between. Now, the concept of a direct substitution, in short, everybody, every function that has been studied in pre-calculus is a continuous function in its domain. And the key is the domain. So you should know what the domain is when you look at a function. For example, example 12, determine C such that P of X is continuous at x equals 5, where P of X is a piecewise defined function and it's equal to x squared minus 25 over x minus 5, when x is not equal to 5, and it's equal to C for x equals 5. Remember, continuity is when the limit and f of a are the same. So first thing first, let's find each one. Let's find the limit. So if I want to find the limit of the function as x approaches 5, by the way, anything other than 5, if you look at this function, this is a rational function, and its rational function is continuous in its entire domain. What is the domain? All real numbers except 5. So from negative to positive infinity except 5. So 5 creates a problem. So let's look at the number 5, therefore. Again, I'll quickly write this for you. This one is a rational function. And its domain, a shorthand notation, everything except 5. Or you may say from negative infinity to 5, union 5 to infinity in an interval format. Okay. So having said that, we are going to take the limit of the function. To take the limit of the function, you can't use x equals 5, but everything except 5. So you take the limit by using the top portion. And the technique, if you plug in, by the way, you get 0 over 0. The technique is factored. The numerator is x squared minus, you can think of this as 5 squared. So x minus 5x plus 5. These two cancel each other. And you get just x plus 5. And if you plug in 5, you get 10. So we proved the limit exists and it's equal to 10. We also know from here that f of a, namely 5, is equal to c, and they must be equal. So the limit of a p of x as x approaches 5 must be equal to the functional value to be continuous. And we know the functional value is given as c. The choice of c must be 10 for this function to be continuous at x equals 5. And again, why are we interested at x equals 5? Because it's continuous everywhere else. Show the function is continuous on negative to positive infinity, where f of x is a piecewise defined function, sine x, if x is less than pi over 4, cosine x, if x is larger than or equal to pi over 4. Please understand that you're dealing with the sinusoidal functions, and each piece is continuous from negative to positive infinity. So the trig functions sine x and cosine x are continuous from negative to positive infinity. That makes this function, the top one is continuous from negative infinity to pi over 4. The bottom one, because it's defined up to pi over 4. The bottom one is continuous from pi over 4 to infinity. Therefore, it makes the function continuous from negative infinity to pi over 4, union pi over 4 to infinity. The end point, namely pi over 4, we are using the parentheses because we don't know. Let's check the end point, pi over 4. If we prove that it's continuous at that point, then it's continuous from negative to positive infinity, as the question is asking up here. So we are going to find the limit of this function as x approaches power from the left. That means we use the top function. Limit of f of x as x approaches power 4 from the left. So you plug in power 4 for sine. As you know, sine of power 4 is square root of 2 over 2. We are going to do the same thing, but from the right. From the right, x larger than power 4, we are going to go with cosine x. So the limit of f of x as x approaches power 4 from the right. That means the limit of cosine x as x approaches power 4 from the right. So if you plug in power 4, cosine of power 4 happen to be square root of 2 over 2 as well. Therefore, because the two are identical, the limit of f of x as x approaches power 4. Okay, and by the way, f of power 4, the functional value, we should know it's square root of 2 over 2. The reason we use cosine, because the equality goes with the second piece. So functional value uses the second piece. So the limit exists, and it's equal to the functional value according to the definition of a continuity. The limit of f of x as x approaches power 4 is f of power 4, which is square root of 2 over 2, and therefore it makes it continuous at pi over 4. And because it's continuous here, adding pi over 4 makes it continuous from negative to positive infinity. So I hope you realize why we had to check the end point, namely pi over 4. Use the intermediate value theorem to show there is a root for this equation sine x equals x squared minus x between 1 and 3. Reminding you of IVT, intermediate value theorem. If f of x is a continuous function on the closed interval of a to b, and let n be any number between f of a and f of b, where the two values are not equal, there must exist a number c in a and b such that f of c equals n. So we are going to bring everything to the same side, doesn't matter left or right. It becomes x squared minus x minus sine x equal to 0. And we call the left side, this side, f of x. Now this function is continuous. Why is that? Because it's a combination of a quadratic function and a sinusoidal function. Both of them are continuous from negative to positive infinity again. It's the sum of QF quadratic function and sine function. By the way, subtract or add sign, it's, remember, subtraction is a form of addition. So that's the first thing, continuous, we prove that. Now the interval given is closed, so let's evaluate it at the end point, see what happens. If you plug in number 1 into this function, okay, you get 1 squared minus 1, they cancel each other, minus sine 1. You don't even have to know, so these two cancel each other because it's 1 minus 1, 1 minus 1. So the answer is negative sine 1, and we should know negative sine 1 is negative because you don't even, that 1 is 1 radian. 1 radian is about 57 degrees, close to 60 degrees. So that's negative. Let's plug in number 3. And that's positive. Let's plug in. When we plug in, this is 9 minus 3 becomes 6 minus sine 3. Remember, sine 3 maximum value is 1. 6 minus 1 makes it 5. So this is definitely positive. So number 0 is somewhere between f of 1 and f of 3. Therefore, there is a root between 1 and 3. I want to make sure you understand what I'm trying to say here. F of 1 happened to be the functional value is something negative. F of 3, the functional value is something positive. So number 0 is between negative and positive along the y-axis. So there must be a root somewhere between these two. So IVT, intermediate value theorem, applies. F of x is a continuous function on the interval of 1 to 3 and has a root in between according to IVT. Limits of functions at infinity. Here's the summary definition. Horizontal asymptote HA of the curve y equals f of x is y equals L. The limit of f of x as x approaches minus infinity is L, or the limit of f of x as x approaches positive infinity is L. That's by definition. 1 over x, if you take a limit as x approaches infinity becomes 0. 1 over x to the power of p, if you take the limit as x approaches infinity is 0 when p is larger than 0. So for both cases, the limit becomes 0, and therefore y equals 0 in both cases would be a horizontal asymptote. For example, we remember the exponential growth, y equals b to the power of x, where b is larger than 1, or exponential decay when b is 0, between 0 and 1, y equals b to the power of x. And the limit, for example, e to the power of x is an exponential growth. The limit of e to the power of x as x approaches minus infinity is 0. The limit of f of x as x approaches infinity is infinity, the first quadrant. And the limit of this function, for example, e to the power minus x as x approaches infinity is 0. And that tells you that these two functions, they have a horizontal asymptote, which is the x-axis. And the equation of the x-axis is y equals 0. And of course, the limit of f of x as x approaches minus infinity is infinity. Those are known as the end behavior. For example, y equals x cubed, the cube function, you remember The limit of f of x as x approaches minus infinity is negative infinity, third quadrant. And the limit of f of x as x approaches infinity is infinity, the first quadrant. And we studied this stuff in algebra known as the end behavior of the graph, and that helps with the graphing. So that's the precise definition of a horizontal asymptote. Infinite limits, vertical asymptotes, short VA. If the limit of f of x as x approaches a, or a from the left, or a from the right, any of them is positive or negative infinity, then the line x equals a represents VA, vertical asymptote. For example, logarithmic functions, y equals ln x. We know that the limit of ln x as x approaches 0 from the right is minus infinity, and that makes VA x equals 0. So pretty straightforward. Everybody knows that, right? By the way, you should know the domain. Domain for the function is 0 to infinity. 0 is not included. Definition of a vertical asymptote VA of the curve y equals f of x is x equals a if the limit of f of x as x approaches a is positive or negative infinity, or limit of f of x as x approaches a from the left is minus infinity, or limit of f of x as x approaches a from the right is plus minus infinity. One of the functions we know, it's y equals tan x. This is y equals tan x. And as you can see, for this function, the limit of tan x as x approaches negative power 2 from the left is negative infinity. So that means x equals minus power 2 is a vertical asymptote. We can see from here the limit of tan x as x approaches power 2 from the right is infinity. And that means x equals power 2 is also a vertical asymptote. And when we go to its inverse, this is y equals tan inverse. So maybe I write this as follows. I write this is y equals tan x. This is y equals tan inverse x. And so as you can see, the limit of tan inverse of x as x approaches minus infinity is negative power 2. And the limit of tan inverse of x as x approaches positive infinity is power 2. It has two horizontal asymptotes because it's the inverse function for tan. Let's continue with finding limits, reminding everybody that if I want to find the limit, I'm going to plug in an observer. When I do that, if I get to a number, I'm done. If I get to 0 over a number, the answer is 0 and I'm done. It's important to know this number can't be 0. If I get to a number over 0, I have to figure out whether it's positive or negative infinity. And if it's 0 over 0, infinity over infinity, infinity minus infinity, and there are many more forms like that, are called indeterminate form. In the case of indeterminate form, in calculus, we come across it often, and they basically mean more work, which means you use your algebraic techniques to figure it out. For example, here, if I plug in, I get infinity over infinity. So the technique is what? Because you're dealing with a rational function, and t or x is approaching infinity, you must divide by highest degree term in the denominator, namely t squared. You do so and you simplify to divide everything by t squared. And it simplifies to the following. Because we can't simplify it further, we are going to plug in 5 over t, 7 over t squared, 2 over t minus 1 over t squared. All of them go to 0 because the denominator is huge. So notice we have 0 plus 0, 1 plus 0 minus 0. Please understand this is 0 over 1, and that is equal to 0. So it's pretty straightforward. We are looking at part B, and if we plug in as t approaches infinity, we get to the same thing, infinity over infinity. Because this is a rational function, and because t is approaching infinity, either infinity or negative infinity, the technique is to divide by highest degree term in the denominator. We must divide by t and simplify. There are 3 terms in the numerator, 2 in the denominator. Each one gets simplified as follows. And now you plug in. This is infinity, this is 2, this goes to 0, this is 5, this goes to 0. Please understand infinity plus 2 or minus 2 or minus 10,000 is infinity. Infinity divided by 5 or multiplied by 5 or divided by 10 billion, it's infinity. If we plug in, we get infinity minus infinity because square root of infinity squared plus 1 is infinity. Okay, square root of infinity even is infinity. Infinity is not a number, is a concept. Okay, and so whenever you have a square root, the technique is to multiply by the conjugate. So what is the conjugate of this piece? Change this to a plus sign. But not only you multiply, you also divide by it because this fraction can't be anything but 1 because you can't just multiply by anything you want. So because it's 1 is acceptable. So for the denominator, you just write it. For the numerator is the product of these two. And you remember a squared minus b squared is a minus b times a plus b. So when we multiply these two, so we get the first one square root of x squared plus 1 squared minus x squared. And this is what we get. X squared plus 1 comes out. X squared and minus x squared cancel each other. And now if you plug in infinity, please understand this means square root of infinity, which is square root of infinity squared plus 1, which is infinity. And infinity and infinity is infinity. 1 over infinity plus infinity is 0. Pretty straightforward. By the way, you may notice, you may have noticed that when we look at this one, the degree, the degree of the numerator is 1, the degree of the denominator is 2 because the degree is smaller, it ends up being 0. But here is larger and it ends up being infinity. It may end up being negative infinity. You have to pay attention to the sign. We'll discuss that in a moment. All right, we want to find the limits here and simply put plug in e to the power of negative t, so negative infinity, that is 0. The reason is because I'm going to remind you, a to the power of minus m is 1 over a to the power of m. This is a negative, one of those negative exponential rules. Therefore, e to the power minus t is 1 over e to the power of t. So this one is 1 over e to the power of infinity, 1 over. So this is 1 over e to the power of infinity, which is 1 over infinity, which is 0. So the answer is 12 over 4 or 3. Part B, we are interested in finding the limit of 5 plus e to the power of t over 4 minus 3 e to the power of t as t approaches infinity. If we plug in, we get 5 plus e to the power of infinity over 4 minus 3 times e to the power of infinity, and we get infinity over negative infinity, which is indeterminate. Please understand this is not a rational function, because rational function means the top and the bottom are both polynomials. They are not. They are transcendental functions. But the methodology is similar. In the case of a rational function, we divide it by highest degree term in the denominator. Over here, we divide by highest value in the denominator, which is e to the power of t. And we simplify. Now, because t is approaching in infinity, e to the power of t goes to infinity. So this is 0, this is 0, 1 over negative 3 or negative 1/3 is the final answer, class. The limit of x squared minus x as x approaches infinity. If we plug in, we get infinity minus infinity, which is indeterminate. So what is the technique? Factoring the x out. Now, if I plug in, I get infinity times infinity minus 1, which is infinity. Previously, when we had infinity minus infinity, we ended up with 0. Now we ended up with infinity, and in some instances, we may end up with a different answer, maybe a number. And it does happen. That's why it's indeterminate. The limit of x squared plus x over 3 minus x as x approaches infinity. And again, if you plug in, you get infinity over negative infinity. And because this is a rational function, everybody, the technique is to divide by highest degree term in the denominator, namely x. So we divide everything by x. And we simplify. So we get infinity plus 1, 0 minus 1. What I want you to be careful is the sign. The top is infinity, the bottom is some negative number. Negative 1 or negative 10,000 makes no difference. Answer is negative infinity. It's important to be able to figure this out. Negative infinity, everybody. And if you look at this rational function, the degree of the numerator is larger than the degree of the denominator, so it ends up being infinity or negative infinity. We want to find the limits, the limit of e to the power minus x plus 2 cosine 3x as x approaches infinity. According to limit laws, we can cut this into two pieces. We are going to write the limit of e to the power minus x as x approaches infinity, plus 2 limit of cosine 3x as x approaches infinity, and we'll see that it does not exist. There is no solution. The reason is very simple, class. This one is e to the power minus infinity, which makes it 0. This part, the limit of cosine, this oscillates between -1 and 1. As you know, cosine, or for that matter, sine, goes between -1 and 1. Because it keeps oscillating, this part doesn't have a solution. Their sum doesn't have a solution. Again, whether it's cosine of x or 3x or 10x, or sine of x or sine of 3x or sine of 10x, sine and cosine, the limit as x goes to infinity doesn't exist. Omega x, let's say. They both oscillate between -1 and 1. Okay. Let me clean up the mess and continue. All right, the limit of e to the power of 3x minus e to the power minus 3x over e to the power of 3x plus e to the power minus 3x as x approaches infinity. Again, it's not a rational function. We treat it as such because if we plug it in, we get infinity over infinity, right? E to the power of 3 times infinity. This is infinity, this is 0, infinity, 0, infinity over infinity. And so the technique is to divide by highest value in the denominator, and I hope you recognize that as e to the power of 3x. So divide everything by e to the power of 3x. What happens? This divided by this is 1, this divided by this is 1. But what about this one? I hope you see that you get e to the power of minus 6x for these two cases. The reason why is, I want to show you, but you should know that. So e to the power of negative 3x divided by e to the power of 3x is e to the power of minus 3x minus 3x by the exponential. Since x is approaching infinity, I hope you understand that this goes to 0, this goes to 0. The answer is 1 over 1 or 1. Find the limits, the limit of tan inverse of ln x as x approaches 0 from the y. Since the limit applies to x, let's put it in and we write tan inverse of limit of ln x as x approaches 0 from the right. We should remember this. And the best way to remember it, remember the graph. So this is what? Negative infinity. Tan inverse of negative infinity. Now, I hope you remember the tan function looking like almost y equals x cubed. Here's the vertical asymptote x equals minus pi over 2. Here's the vertical asymptote x equals pi over 2. So write this one, tan inverse of minus infinity, that means pi over 2. Or if you go with this one, you should recognize the answer is as the minus infinity, the answer is negative pi over 2. So I've given you several graphs because graphs will help you see the answer. The limit of sine squared over x squared plus 1. I remind you of the squeeze theorem that if a function is between two functions and each of them on the left and right side have the same limit, the one in the middle will end up with the same limit. And whenever we have a very complicated limit where somehow it involves sine and cosine, actually it makes life easy because we know sine is between -1 and 1. Remember, we want to get this expression from here. We want to get to this expression. The first thing is to square it. Again, when you square it, please understand 1 squared is 1. But this one, -1 squared is also 1. So it's 0. If by any chance it was -2, then it can go all the way to 4, by the way. If this was -2, when you square it, you get +4. So it goes from 0 to 4. Okay. Now we want to make it look like that. So all you have to do, multiply by 1 over x squared plus 1. If I multiply by 1 over x squared plus 1, it will look like that. And before I multiply, because x is approaching infinity, this, and even if it was not infinity, this expression is positive because it x squared makes it positive, right? And plus 1. So it doesn't change the sign. It won't flip over. Remember, if you multiply by negative, the signs will flip over. So this expression in the middle is between 0 times this, which is 0, and 1 times this, which is this. And we take the limit of both sides, the left side and the right side, as x approaches infinity. This one is 0. You don't have to do anything. This one, as x approaches 0, is also 0. So this one is 0. This expression, when x approaches infinity, I hope you know, is 0. So if the left and right, f of x and h of x, result in the same thing, the middle one also, by the squeeze theorem, the limit of sine squared over x squared plus 1 as x approaches infinity is 0. And you must mention y by the squeeze theorem. F of x is 2x squared plus 1 over 3x squared plus 2x minus 1, and we are to find asymptotes, which means we are dealing with a rational expression, or in this case, rational equation or rational function. To find asymptotes, we are interested in finding horizontal asymptote and vertical asymptote. To find the horizontal asymptote, we take a limit as x approaches infinity or negative infinity. You really have to do both. Sometimes they produce different answers. In this case, makes no difference. Remember the technique. You're dealing with a rational function. X is either approaching infinity or negative infinity, makes no difference. The technique is to divide by highest degree in the denominator, which is x squared. So we divide everything by x squared. And we simplify. So we get 2 plus 1 over x squared, we get 3 plus 2 over x minus 1 over x squared. Because x is approaching infinity or negative infinity, this goes to 0, this goes to 0, this goes to 0. The answer is 2/3, which means horizontal asymptote has the equation y equals 2/3. Now, if you go back here, you notice the degree of the numerator and the top and the denominator are the same, so this 2 take over becomes 2/3. But the justification is the process that you see. Vertical asymptote, remember when the limit approaches infinity or negative infinity, x equals a is that. And one easy way is to set the denominator equal to 0. That's how we did that. Previously, you can do the same thing. Now, this is an easy factoring because 3 is a prime number. So x and 3x, and this is -1. So you have to go with -1 and +1, such that the middle term, take a look at the middle term of it. This is minus x. This is 3x. They add up to 2x. So you have to check the middle term. If you set the first one equal to 0, x equal 1/3. And if you set the second one equal to 0, x equals -1. And those are the VAs, vertical asymptotes, x equals 1/3, x equals -1. Find the formula for a function that has vertical asymptote x equals 1, x equals 3, and horizontal asymptote y equals 1. So the reason we say find a formula because it's not unique, you can find different formulas. So let's look at the case and see what we have here. So one possibility is we have the vertical asymptote x equals 1, so we need to have x minus 1 in the denominator. And we have x equals 3, so we need x minus 3 in the denominator. So I hope everybody is clear as to why we are coming up with those, okay? So we need that. And then horizontal asymptote y equals 1. If you multiply these two, you get x squared and the rest is not important. And because you want the horizontal asymptote, so let me just write that. If you multiply them out, you get x squared. And even if you don't find the rest is not important. The highest degree term in the denominator is x squared. So we need the x squared in the numerator. And the coefficient must be 1 because y equals 1. Let's say y was 5, you would put 5x squared. This is one way to do it. If I said x squared minus 1 or x squared, not minus 1 because it has x minus 1 in it. X squared, let's say plus 7. Let's just make it up. If we said another possibility is x squared plus 7, don't change the denominator. That's just as good. So it's not unique, and this is one way to come up with the answer.